Let's evaluate in detail gain and phase margins using the delta uncertainty model produced in the last video. Here's our Nyquist diagram and a hypothetical loop gain. The loop gain evaluated at omega 1, having phase minus 180 degrees. We're at the critical point for that phasor if we multiply that loop gain by a factor of minus 1 over LU evaluated at omega 1. That's our gain margin. Clearly, that makes the phasor equal to minus 1. The magnitude of the phasor is 1 over the gain margin itself. So we'd like to determine K star, the gain margin, using this delta uncertainty model that contains a gain and phase uncertainty, K and theta, respectively. So first start with the loop gain at omega 1, which is just the gain or the controller K and the plant P at omega 1 multiplied together. And then breaking the loop at the plant input between the disturbance delta and the plant, we get the following loop gain L prime. And note that we're just scaling the loop gain. So we'll set phase equal to 0 and just look for that factor K that causes LU at omega 1 to be equal to minus 1. Substituting an Euler's formula for the exponent. Set an equal to minus 1, looking for K star, and also substituting in theta equals 0. Simply left with K star LU j omega 1 is equal to minus 1. And so simply solving for K star, we obtain an expression for the gain margin. The frequency omega 1 is called the phase crossover frequency. That's where the phase crosses the minus 180 degree line. So to determine the gain margin, we need to determine the loop gain at the phase crossover frequency. Now let's determine the phase margin. That's theta star, again with the delta uncertainty model. And going back to our Nyquist, put a part of the unit disk there, and then the phasor with unit magnitude at omega 2, frequency omega 2. So if that phasor is rotated by theta star, then the loop gain is on the critical point, and that theta rotation corresponds to the phase margin. So note that the magnitude of the loop gain for all theta is 1 at omega 2, for all theta uncertainty we may insert. And that theta that we're inserting is a rotation of the loop gain about the origin. And we're looking for that theta star that makes the loop gain evaluated at omega 2 equal to minus 1 again. So of course we're going to set the gain equal to 1, and then we just have e to the j theta times the loop gain at j omega 2. Euler's formula. And then the loop gain at omega 2 has both real and imaginary part, and we set that equal to 1. And by doing that, we can solve then for theta star. Expanding just into real and imaginary components now. Since k is 1, the loop gain at j omega 2 will always be 1. We need to make sure to select theta star so that the imaginary component is 0. So let's focus on making that term true. Imaginary component set equal to 0, and then just solving for theta star. And finally, our expression for phase margin. The phase margin theta star requires us to determine the loop gain at the crossover frequency omega 2. Omega 2 is the loop gain crossover frequency because it's the value of the loop gain magnitude when it's 0 dB. So it's the loop gain transfer function crossing the 0 dB line at omega 2. And we've looked at this with Nyquist so far, but it's insightful to bring it all together with Bode plots. On top, the magnitude of the loop gain in decibels, and on bottom, the phase angle of the loop gain in degrees. Here's our 0 dB line. We cross that, we have the loop gain crossover, and there's the minus 180 degree line. When the curve crosses that one, it's the phase crossover. And since we're working with decibels, we need to recall the formula for decibels. And then just for comparison, again, here's our Nyquist diagram with the phasors associated with the loop gain and the gain margin and the phase margin. So some hypothetical loop gain, it's strictly proper, so it'll have negative slope. This is just to illustrate how to read margins from the Bode plot, connecting it to the Nyquist. We won't be concerned with the slope of the loop gain and decibels per decade and all that. We haven't said anything about the form of the loop gain transfer function, except that obviously it's strictly proper here. So bringing down the line from the crossover frequency, that's the loop gain with magnitude 1 on the unit disk, we get a margin between the phase angle of the loop gain and the minus 180 degree line there. So that's theta star. And then at minus 180 degrees, we have another margin. That's the phase crossover. And then we zoom in on the loop gain, and we have that little margin there between the loop gain and the 0 dB line. That's the margin between the loop gain on the Nyquist diagram and the minus 1. But we're working on a Cartesian coordinate system here in a linear scale, And the Bode is in decibels, so to determine what that delta is in the Bode diagram, we'll need to determine the gain margin in terms of decibels. So there's our formula for the gain margin. And since it's pure real, we'll just use the pure real component of LU. Note that A1 is negative, so that K star is positive. And then K star in decibels. Leaving just minus the loop gain evaluated at the phase crossover in decibels. The magnitude of the loop gain evaluated at the phase crossover in decibels. Well, the magnitude of minus the magnitude of the loop gain is simply that margin right there. So the margin in decibels between the loop gain and the 0 dB line at omega 1 is the gain margin. And so here's just a visual review of what we've done. Started with determining the gain margin, the Nyquist, looked at the phasor at minus 180 degrees and put a delta uncertainty model in there. And setting theta equal to 0, solve for K star. That would make the loop gain at that frequency minus 1. And then the same thing for theta star. Just a little trig, getting the formula for the phase margin. And then making the connections between these margins on Bode and the margins in Nyquist. Two key frequencies in this, the loop gain crossover and the phase crossover frequency. Getting the gain margin required us to transform K star into decibels. And so in doing that, we determine that the margin between the loop gain and the 0 dB line is K star. And that is classical stability margins for gain and phase.